Right, back to it. Let's do that later. Okay, so we've talked about how to get the ortho position selectively. We've talked about how to get through to the para position selectively. And really that leaves just one, meta. And we know that we can do that with electron withdrawing groups using electrophilic aromatic substitution. But the problem with an electron withdrawing group is that it also deactivates your molecule to reactions with electrophilic aromatic substitution because there's less electrons to go around. So often meta-reactivity is quite difficult to attain for that reason, and sometimes the functional groups are just all wrong. So we're going to now do a strategy called benzyne formation. Okay, so here we go. We start with orthochloroanisole, okay, which is easily made by electrophilic aromatic substitution. Okay, orthoselective, or of course you could even make this product by doing ortholithiation and then addition of a chlorine source. So we need a strong base for benzyne formation, and the classic bases for this are actually N- amide bases. So this is sodium amide. NaNH2. You can buy sodium amide from Sigma Aldrich or other suppliers, of course, or you can dissolve sodium in liquid ammonia and wait a while. Sodium in liquid ammonia gives you a bright blue solution because essentially you have dissolved electrons. As that solution ages, those electrons start to react with the ammonia, you give off hydrogen gas, and you generate sodium amide. So, the sodium attacks the hydrogen, and you actually get an E2 elimination. Okay? So, E2 syn elimination. That generates a benzyne. Okay, so this is often drawn like this. Okay, where you've actually got a triple bond in the ring. Okay, this is incredibly reactive, it's incredibly strained, and it's not really a proper triple bond. Okay, it's not anywhere near as strong because of the ring strain, because of the distortion that is put into the ring. So what we've shown here is the LUMO, the pi star of the benzyne, and that means that we can get attack into this lobe of the orbital or this lobe here. But the key thing here is that attack happens in the plane of the ring. Okay, it's not above the ring or below the ring like you see in electrophilic aromatic substitution or nucleophilic aromatic substitution. It actually attacks in the sigma plane of the ring. So when we do this deprotonation, this E2 elimination, we generate the alkyne, and that is the only benzyne that we can form here. Okay, there's no other protons that we could have deprotonated to get through to this. Okay, and then the sodium amide, of which we're using it in excess, can then attack, and it attacks at the less hindered position, but also it attacks in such a way as to generate an anion. Don't forget there's the sodium plus, and that is stabilized by coordination to the methoxy. The anion is stabilized by methoxy group. And then H plus on workup gives you the meta product. Okay? Only meta NH2 produced. Okay? What's really interesting, though, is that you could not make this product by SNAR. Oh, not just by SNAR, by SEAR. Okay? The way that you normally make an aniline on a benzene ring is to make a nitro group and then reduce it down. But the methoxy directs ortho or para. So you could make, using electrophilic aromatic substitution, the ortho aniline or the para aniline, but you could not make the meta. You have to go through a weird strategy like this. So mechanistically, this all makes sense, though generation of an alkyne in a benzene ring sounds pretty peculiar. So how do we know that this is formed? Well, here is a different strategy for making a benzyne. You take an ortho amino acid here, and then you use diazotization conditions. Which turns the aniline into an N2 plus leaving group. Okay? That's semi-stable. You get some positive, negative charge stabilization. But if you heat it up a little bit, you lose carbon dioxide and you kick out nitrogen gas. Okay, so that is obviously entropically very favored, producing two equivalents of gas. Now, if you just leave that on its own, what ends up happening is that you get plus CO2 plus N2, you get dimerization. Okay, you get a 2+2 reaction, and that gives you this product here. And so if you do this reaction, leave it, let it warm up, and then you take a sample and throw it into the mass spec, this is what you see as the main peak at 152 units. Okay. However, an alternative way to try and prove that the benzyne was formed is that you show it doing reactions that you know alkynes or alkenes could do. So in the presence of furan, you heat it up and it undergoes a Diels-Alder reaction. Okay, so we can show that happening like this. It does the 4+2 reaction, and it generates a product that we know has to form from a reaction with a double bond. A double bond that has to be orthogonal to the benzene ring, because the benzene ring does not do Diels-Alder reactions. So through these various kinds of processes, you can prove that a benzyne is formed. Okay. This is, of course, quite related to the ortho lithiation because you're using strong base. So let's go for an entirely different idea next. Okay, and everyone who knows me just a little bit knows that I do like my pericyclic reactions. So here comes the first one. Okay, the Claisen rearrangement. This is awesome. Okay, this is a really clever, really old reaction, and I will talk quite a lot about this during the course in various different forms. But here we have an intramolecular rearrangement. Okay, so you can take a phenol, you react it in the presence of base with an allylic bromide. Okay, so it can do a substitution of the bromine. It can either do direct substitution like this, or it can react at the other end and the arrows hook up together that way. Either way, because allyl bromide is symmetrical, we get the same product. The Claisen rearrangement itself, that happens in SN2, and the Claisen rearrangement itself is when you heat this quite a bit, you get a cyclic transition state, a cyclic mechanism that breaks aromaticity initially to give this diene ketone. And very unsurprisingly, loss of H plus, gain of H plus, rearomatizes to the phenol. Okay, it's very rare for these products to stay around any length of time, but sometimes you can actually interrupt this reaction and get something other than the aromatic product. Okay, now, just going to mention, like I said earlier, it is actually quite difficult to see whether it goes SN2, like I've shown here, or it could attack at the opposite end of the alkene like this. When this happens, it's referred to as an SN2 prime reaction. Whenever you have a prime reaction like this, it usually means that there's an alkene in the middle involved. So, for example, if you took that and you treated that with base, you would get butadiene, and that would be an E2 prime reaction. In the case of allyl bromide, it can't easily tell which end of molecule reacts. Both SN1 and SN2 can be very fast. Okay, I'm not going to discuss the Woodward-Hoffmann rules regarding this process very much, other than to say that it is allowed. And it goes through a chair transition state. We will talk about chair transition states another time. So, yep.
Quick question. Is it fair to say, okay, so pericyclic process, all of those electron movements happen together at once? Or
if
is there
a true pericyclic process, those electron movements must happen at the same time. That the characteristic of a pericyclic reaction is that you have, firstly, a cyclic transition state where the electrons flow in a single step. Okay, so
okay. So we don't say, okay, the process begins here and here. We just say it's had that chair conformation. it's able to do that cyclic cyclation.
Yeah, so I'm just gonna, yes, I want to keep those. So if I create, I just add in a new slide here. We can show, classically we do a Diels-Alder reaction. And if I draw it like this, so 3 arrows, 1 step. I get my cyclohexene. Okay. Now, if I had a very similar reaction here, same aldehyde, but the diene is different, what ends up happening actually is that it actually does a conjugate addition. Like that. And then the enolate actually does a manic reaction like that. So it looks like it's done the same kind of reaction between these two, but the top one is pericyclic. It's a concerted process. One step cyclic transition state. Nope. This is 2 steps, not a cyclic TS. So it is not a pericyclic. Make sense?
Yes, thank you for the clarification.
Okay, my pleasure. So Kleisner rearrangement, fine, cool, whatever. But in that previous example, I could have just as easily done an ortholithiation and attacked allyl bromide. So why did I mess around doing pericyclic reactions? Other, of course, than the fact that I love pericyclic reactions. Well, it's because it allows you to do some really funky stuff. For example, here. So here we have prenyl bromide. Now it's a lot easier to tell whether it goes by SN1 or SN2 or SN2 prime. It goes by SN2. Okay. So steric hindrance favors SN2 instead of SN2 prime. Okay, pretty obvious. Primary site versus a tertiary site. Then, when it what's going on here? The arrows are in the wrong direction. That makes okay. So sorry about that. Okay, so base deprotonation SN2 instead of SN2 prime, and then we get our what happened now? Then we get our pericyclic rearrangement. Now, when we're drawing a pericyclic rearrangement, currently I'm drawing the arrows going clockwise, anti-clockwise. I could just have easily have drawn them going clockwise. There is no difference as far as a pericyclic reaction goes. because it's all about the orbitals, not about the magical curly arrows. So we draw our rearrangement, and then, of course, we re-aromatize as before. And you can see that now we've gotten a product where the bulky groups are close to the ring, not removed from them. If you considered doing this reaction by ortholithiation, let's say we have the O-methoxy there, lithium, and we tried reacting that with prenyl bromide, it would react to give the less hindered product. So depending on how we do this reaction, because we do 2 steps versus the 1 step of the lithiation, we essentially invert the steric requirements of the reaction. So we can deliberately get very hindered products that it would be impossible to get by other methods, because we form the less hindered bond first, and then we rearrange to put the more hindered end onto our ring. Okay. So it gives the more hindered product. Yay. It's very annoying, but the more hindered product is often very, very useful and consequently very, very hard to get. So, allylation. Let's talk about it a bit more generally, okay? If we want to get this product here with the less hindered nucleophile attacking, we can actually use 2 different starting materials, because we could either get the more hindered bromide, shown here, and do an SN2 prime reaction, or we could start from the more hindered bromide, the less hindered bromide, and just do a standard SN2. Both things give the same product. Oop. So we get the same product regardless of which allylic bromide is used. Now, if you have an allylic alcohol like this, and you could make that easy enough by adding vinyl magnesium bromide to acetaldehyde, for example, these products are actually unstable in acid, okay? Because acid allows us to do a kind of SN1 reaction. Okay, so we protonate our alcohol and then we lose water as a leaving group. We get through to an allyl cation, which could then be attacked at either end, and it's going to preferentially attack at the less hindered end. And then we lose proton again to get the less hindered product. Now, if you started with this alcohol on the right and treated that with acid, and if this was absolutely pure, you would end up with a small quantity of the alcohol on the left. The one on the right is the thermodynamic product, but the thermodynamic product means it's the most favorable. It doesn't mean it's the only. Okay, so you would get the same product mixture from either alcohol starting material. And you can see this happening when you treat these alcohols with HBr. So the primary bromide here favored because it has the more substituted alkene and less hindered Br. We get through to this product mixture, the 13 to 20 and 80 to 87, through the same allylic cation as we did in the first case. So the primary bromide is favored, but it isn't the only thing that's present in the reaction mixture. Now, that's when you're looking at allyl halides, allyl alcohols. But what about if we made a Grignard reagent from these bromides? Well, a lot of the same things can happen. So we start with the more favorable bromide and we react it with magnesium. And because we say that alkyl groups are electron donating, having the magnesium at the least hindered position is going to be favorable because that's going to be more stable. The less substituted anion, more favorable. So just to give you some numbers for that, we said before, remember, that N-butyl lithium, the corresponding pKa is around 48. If we're looking at tert-butyl lithium, the pKa is around 54, I think. Okay, so the more substituted an anion, the less stable it is. The less substituted an anion, the more stable it is. And these two can rearrange through what it says here, probably an eta3 allyl anion complex. Okay, so that is the anion there and the Mg plus sitting on top of it. Okay, so let's look at electrophilic substitution with carbonyls. So I know you're a lot more used to nucleophilic substitution, but we can do electrophilic too. So we take our less hindered bromide, react it with magnesium, and then we react the Grignard reagent with carbon dioxide. And interestingly, we get the more hindered carboxylic acid out. Now remember, it doesn't matter if we started with the less hindered bromide or the more hindered bromide. Number one, they rearrange anyway. But number two, the magnesium would give the same Grignard in both cases. So we react our bromide with magnesium, as we're showing here. The magnesium Grignard is shown. The magnesium can then act as a Lewis acid to coordinate this oxygen, and then it attacks here. So it attacks at the carbon of the CO2, breaking one of the carbon-oxygen double bonds to give the internal acid here, which upon protonation gives the carboxylic acid. Now we could get the other product by using a cyanide source. Oh, dear me. Didn't mean to do that. So, if you take the bromide mixture, remember it's a mixture, oh, for goodness sake, sorry. Take copper cyanide as our cyanide source. It does an SN2 on both of these, in actual fact. And you get primarily the less hindered one, because it does SN2 on both, but it can also do SN2 prime, and it mostly does SN2 plus SN2 prime on the first one, and just SN2 on the second one. So we get a different product mixture than we started with because of that, and then concentrated HCl to hydrolyze. And this isn't a typo. Note the less hindered nitrile is preferentially hydrolyzed. Okay, so we're actually able to separate these compounds very easily by doing a base extraction and then back extract into organic. So, somewhat surprising, but you can actually get both compounds that you might want, but it just is all about how you understand which mechanism is operation and which compound you want. Okay, so more about this allylation problem and the Claisen rearrangement. So, we said before that we can get SN2 or SN2 prime happening, and allylic bromides can rearrange quite easily. As a result, we get about 1% of this and 99% of this in any bottle of prenyl bromide that you buy. It typically only reacts on this end, but a little bit goes backwards and forwards because it goes through SN1 because you have a very stable tertiary cation formed. And like we said before, 80 to 87% of this, 13 to 20% of this. So, if I wanted to selectively get this product or this product, maybe, trying to just do attack an alkylation using an enolate might be a problem. So, one way that we could say hopefully this work is maybe SN2, maybe at less hindered end. So we take our ketone here, acetone. We can use LDA, which is lithium diisopropyl amide. And then we could hope that that then does SN2 to give our desired product. What about if we want to get the more hindered product, though? What do we do then? Well, maybe we could do that under more cationic conditions. SN1 for more hindered product. Question mark, question mark. The way that we'd do that is we'd use TMS chloride and triethylamine to make the TMS enol ether. And then maybe if we formed the cation in the presence of the Lewis acid, then it would react hopefully at the more cationic site. Maybe. So, how could we actually stop saying maybe quite so much and actually get the product that we want? Well, obviously pericyclic reactions can come to our rescue here. So, remember that allylic alcohols only equilibrate in strong acid. So, if instead we use a weak acid, which is traditionally propionic acid, which is a weak acid, like I said, then we can generate, in the presence of this acetal, we can use this alcohol first to make a mixed acetal, and then in the presence of more acid, we can protonate our methoxy, kick it out, and finally generate an alkyl vinyl ether, shown here. Then, rather than the aromatic Claisen rearrangement that we did before, we do our Claisen rearrangement again. Okay, and this is now an aliphatic Claisen rearrangement. So, weak acid for acetal equilibration, and then heat for the rearrangement. Because we have a carbonyl here, we've exchanged two alkenes for one alkene and a carbonyl. Obviously, our product is favored because we said at the very start of this lecture that the carbonyl is stronger than an alkene. So we turn the alcohol inside out and we can get our desired more hindered substitution product. Instead of starting from an acetal, we can also start from a vinyl ether like this. Again, use some dry acid so that we don't hydrolyze the enol ether, and again rearrange as before. Okay, so this kind of rearrangement is actually given another name. So if you take a hindered alcohol like we have here, and we react it with a standard acetal, and we do the rearrangement, then it's just the Claisen rearrangement. However, if you start with an orthoester, so it's got the 3 methoxy groups on there, then you get through to this compound. Again, this is in the presence of propionic acid. You get out an alkene and an ester now, and this is sometimes called the Johnson Claisen. For the ester, or we can create this acetal of DMF. This is often referred to, it's an acetal of DMA, dimethylacetamide. So this is often referred to as DMF, DMA. No, sorry, DMA, DMA. My apologies. Dimethylacetamide, dimethylacetal. So we can take this reagent, again we react with propionic acid, and we get out the same kind of intermediate. Once again, we can still do our Claisen as before. It's just now that this is referred to as an Eschenmoser Claisen, and that makes the amide. Now, the thing I want you to notice in all of these cases one, two, three, all give the trans alkene. Ooh, what's going on today? Which is the E alkene. Now, this can be explained because in all of these cases, we've only got one R group. There's only one thing exo to our ring that changes, that is at a tetrahedral center. And when we draw this, I'm going to draw this as an up. This H is up. When we draw our reaction in 3D, we draw this as a chair transition state. The H goes into the axial position. The R goes into a pseudo-equatorial position. Okay, the R group equatorial. And then we do our rearrangement as before. Our transition state has the bonds being both formed and broken at the same time and gives us our desired product. But the key thing is that you can see here where the alkene is going to start forming, these true groups here are trans to each other. So we end up with a trans alkene. So sorry, just got an email. Let's do some examples now. So first of all, we're going to do a Johnson-Claisen. And what's nice about this, of course, is that you have firstly a selective regioselective reduction. And it is regioselective because 1,4 addition is hindered because you've got those methyl groups. So we get regioselective for our first reduction. Then we react with the orthoester like we did before, and you heat it up, and we get this chain extension to generate this ester, but we get the ester added onto this carbon, which is, of course, the more hindered one. We could not do that through an SN2 reaction. Okay, we couldn't take ethyl acetate here, try and make this molecule at the top, and try and do an SN2 there. We couldn't do an SN1 for sure. If we tried to do this reaction, it would attack here, so it would not give us our desired product. SN2, not going to work. Okay, so the Claisen reaction here gives us the ability to do this reaction that we would not be able to do otherwise. Now, what's being shown here is a fragment of a natural product called Brefeldin A. I have not looked that one up, but if you want to, go for it. If I remember correctly, it's relatively big. And we do the exact same kind of idea. We use the orthoester as before. Phenol is being used as the weak acid here, so it's a very weak acid, and it's being heated to 125 degrees. We get through to the same intermediate. We rearrange and we get the trans alkene out. But importantly, in addition to getting our trans alkene, we actually get a transfer of stereochemistry. Okay? Okay? The reason that this works is that when we draw our molecule in a chair transition state structure, well, I'm going to call this bit here R, and this bit on the side here as R prime. Okay, so we're putting R prime into our pseudo equatorial position, and R is going where it goes because it's on the other end of a trans double bond. Okay, this is trans, and it is trans here. So when we do our rearrangement, we form this new bond here, and the ester is on the same side as it was when it started. Okay, I'm just going to draw that in purple. There we go. Purple there, purple there. So it ends up being down here and down here. Now, there are relatively many ways to do reductions selectively, or there are even ways like opening epoxides that we can make alcohols with stereochemical information there. Making carbon-carbon bonds with selectively is a tougher process. So what is really impressive about this version of the Claisen rearrangement, and one that we will come to in a couple of weeks called the Ireland Claisen, is that they are really good at transferring easy to make or comparatively easy to make carbon-oxygen stereochemistry into carbon-carbon stereochemistry. Okay, so all stereochemistry comes from the well-defined chair transition state. I will just mention as well that technically there are 3 alcohol moieties within our starting material, but both of them here have been protected. We've only got 1 free alcohol that can react. Okay. So, next up, chemoselectivity. Okay, we've done a whole bunch of regioselectivity now, and it's time to start doing some chemoselectivity. And so the first bit of chemoselectivity we're going to be doing is oxidations. Okay, so a reaction that I'm sure everyone knows, epoxidation. A reaction that probably not everyone knows, the Baeyer-Villiger oxidation. Okay, now typically you use the same reagent for both, hence why we need to understand the chemoselectivity of this. So we take a per acid in both cases. And a per acid, well, you know that that is an acid, a carboxylic acid, and a per acid has an OO bond present. Okay. Now, the way that you often see per acids drawn is the way that I've drawn them here. Okay, they have an intramolecular hydrogen bond that makes them have this kind of ring-like structure. And when you're showing an epoxidation, that is actually very important because you get a bicyclic transition state that's often referred to as being like a butterfly. I don't quite see it personally, but sure. Anyway, we can draw our mechanism arrows like this. Remember, the alkene is nucleophilic. We said that at the start. The OO is electrophilic. Okay. So the carbon-carbon double bond attacks the OO single bond, breaks that bond, and the electrons keep flowing around. And that oxygen, which remember is involved in a hydrogen bond, that hydrogen starts to deprotonate that hydrogen bond. And at the same time, those electrons then attack to the other end of the double bond. Okay? Doesn't matter which way around we draw this, we end up with these bonds being formed at the same time as this bond being broken and the oxygen transferring. So we end up with this epoxide. Okay. The Biovilliger reaction, well, we get our per acid and the terminal oxygen attacks and protons transfer around the place. We then get our oxidation step, okay? Here, the oxygen kicks down, or you can say that the OH bond does it, and the carbon-carbon bond here moves onto the oxygen. As that attacks, the OO bond breaks, and you can either show that electron going onto the oxygen, or let's go all the way around and then have that take off the H. So electron density starts to build up on these two oxygens. These two oxygens, however, start to feel some positive charge building up because they're losing electron density as this goes on. Okay, but again, we have a broadly cyclic transition state, and we end up with an ester at the end. So the carbonyl is still there, but now it's part of a larger functional group, the ester. Okay. Now, in both cases, the rate determining step involves nucleophilic attack upon the oxygen-oxygen bond. Okay, the slow steps both use the OO sigma star as the LUMO. Okay, the electrophilic step is the same. And we're very used to using MCPBA, which remember is meta, oh good grief, which is meta chloro per benzoic acid. That's the most common one. It isn't necessarily the best, but it is pretty stable and you can buy it, which makes it the most common. Trifluoro peracetic acid is actually the best reagent. Unfortunately, it is the best reagent for both of these reactions. So we cannot easily achieve chemoselectivity by reagent choice. Yeah, goodness me. It all gets a little bit more complicated. We need to think a bit more about which functional group might be more reactive and why. So let's look at the reaction taking place between these two substrates, this one down here and this one up here. Okay, now hopefully that you can see these two substrates are quite similar. They both have a ketone, they both have an alkene. Which one reacts in which direction? Well, we have a normal ketone here, okay, in our first substrate. Okay, And the reason that we're going to call it normal is that when we look at this substrate under IR, we see a stretching frequency for the ketone, which is nu tilde max of 1715 wave numbers. Okay, that is the standard value for an unstrained ketone. Okay, ring strain or other effects change that. Okay, so 1715 centimeters, normal ketone, nothing special about it. And what we find is that when we have a normal ketone and an electron-rich alkene, and it's electron-rich because it is tri-substituted. Then in actual fact, we get the epoxide. Okay? The alkene is particularly good for epoxidation, and there is nothing special about the ketone. So, the alkene is what reacts. Now, let's look at our second substrate. Now we have a di-substituted alkene. So the alkene is less reactive than it was when it was tri-substituted. The ketone is strained. And we know that by using IR again. So lambda max, sorry, no, nu max, nu tilde max, in this case, is 1745 centimeters. Okay. The alkene is also slightly strained, but it isn't very strained compared to the ketone. So now the ketone reacts. Okay. So if there is some strain onto a ketone, then that will favor getting the Biovilliger oxidation rather than epoxidation. Now, that isn't necessarily something that you can easily predict. Sometimes you can, but experimentally, if you can do an IR of your compound, then you might actually be able to know which way your compound is going to react. So let's look at our third substrate now. This one's a bit special because now our nu tilde is 1780 centimeters to the -1. It is a very strained ketone. So it is very strained, and what happens is that when you attack, because remember, the ideal bond angle here is 120 degrees. Okay? Here, of course, it is 90 degrees. Now, if you have an acetal, or, you know, a hemiacetal where we've attacked with our peracid, the desired bond angle is 109 degrees, 28 minutes. Okay, that's the tetrahedral angle. So when you get attack of one of your oxygens onto the ketone, you immediately relieve strain, which is a good thing. And once you've done that, you are promoting your Biovilliger oxidation. So, very strained ketone has strain relieved in rate determining step. the alkene is disubstituted, but there's nothing wrong with epoxidation. So if you have two equivalents of MCPBA, you will do the epoxidation as well, but the strain on the ketone is severe and it will react there first. Now, note that we actually have, when we get through to our intermediate here, JJH alkene, there are two possible groups that could migrate. Okay, this could migrate, or this one could migrate. Regioselective question. And it is regioselective for the more substituted carbon atom. Okay, so the only product that you get from the Biovilliger oxidation is insertion into this red bond. Okay, and that's because in the transition state that we showed on the previous page here, we get buildup of positive charge near the carbon. So the more substituted the carbon, the more likely it is to migrate because it can stabilize that positive charge a lot better. So, talking about the Biovilliger oxidation gives me thoughts towards something that is slightly related to this kind of compound. Okay, and this is the alpha effect. Okay, the alpha effect is something that we use to explain the reactivity of some very reactive molecules. So, some unusually reactive and specifically nucleophilic species. We're talking here about hydrazine. We're talking about hydroxylamine. And we're talking about hydrogen peroxide. And yes, to some extent, we are talking about peracids here. Now, these compounds are substantially more reactive than the corresponding amine for alcohol. Okay, but they are less basic. Okay, we often say that good, strong bases are strong nucleophiles and weak nucleophiles are also weak bases. But in this case, we're actually finding something that is more nucleophilic than the pKa says it should be. So, if you consider ammonia, the NH3 plus H plus goes to NH4 plus. Well, the pKa H of this process, which is actually the reverse, is 9.25. Consider hydrazine. The pKa H is 8.10. So based on the pKa value, you would naturally say that hydrazine is going to be less nucleophilic than ammonia, but it is completely the opposite. Ammonia is much less nucleophilic than hydrazine. Now, the explanation for this is this alpha effect. It is a molecular orbital effect. So, when two small, which is to say second period, elements with lone pairs are bonded to each other, the lone pairs are so close they have to interact. Okay, so we can draw this as an energy diagram like this, where we have nitrogen and another nitrogen here, and both of these orbitals are filled. These are sp3 orbitals. And as normal, you form a bonding and an anti-bonding combination. But both of them are filled. What this means is that we have a new higher energy HOMO. And the difference here is the difference between ammonia, if you like, and hydrazine. Okay, this is the energy of nitrogen lone pair. So, when it comes to the reaction between two molecules, you're usually looking at the interaction between the highest energy HOMO and the lowest energy LUMO. And here we've produced a high energy HOMO. That means it is more nucleophilic. This is broadly a kinetic effect because it's all about that fast interaction between the high energy HOMO and the LUMO. So remember, for reactivity, you want a high HOMO and a low LUMO. Those two things give a good energy match. Okay. Typically, LUMO, the lowest unoccupied molecular orbital, is often an antibonding orbital. Antibonding orbitals are very high in energy. So anything you can do to bring that down in energy will help. Conversely, HOMOs are either lone pairs or they're bonds or bonding orbitals. That makes them lower in energy. So if we want anything to happen, we're going to need the highest energy HOMO we can and the lowest energy LUMO. So that brings us to 434. I'm going to just do one more slide as we started 5 minutes late and had a break. So here we can show chemoselectivity and regioselectivity based on some reaction conditions. And you can see here we have our alpha effect in operation. So if we take this alpha beta unsaturated ketone here, now we're not looking at two different functional groups. We're looking at a single functional group because when the alkene is conjugated to the ketone, they react together somehow. Okay, so if we take hydrogen peroxide in base, then what we're actually getting is a truly nucleophilic reagent. Okay, it's nucleophile minus. And the true reagent is actually hydrogen peroxide anion. So the alpha effect raises HOMO energy as does deprotonation. Okay, so then the mechanism of this is that O minus attacks in a conjugate fashion. Okay, it's a much better nucleophile than it is a base because of the high energy HOMO. Oh, dear me. So conjugate addition to generate the enolate. The enolate then comes back down and attacks the oxygen. The oxygen is electrophilic because of the weak OO bond. Weak OO bond makes oxygen 1, and I'm going to say that's oxygen 1, that's oxygen 2, an electrophile. Okay, now you may have been told in your first or second years of undergrad that hydroxide is a terrible leaving group. It is. It is a terrible leaving group. This is one of the very few reactions where you will ever see OH minus as a leaving group. But the reason it leaves here is because the OO bond is so weak that it just wants to leave. Okay? So we get this chemoselective epoxidation here. Okay? Because we use H2O2. Okay? And this is sometimes referred to as the White's-Sheffer. That's two F's. Oxidation. Now, if instead of doing this reaction in base, we instead do it in the presence of acetic acid, what ends up happening is that H2O2 plus acetic acid gives water and peracetic acid. So the true reagent here is actually electrophilic, and it's actually, like I just drew up there, the per acid. And therefore the per acid here does the Baeyer-Villiger oxidation. instead. Okay. So we can actually do some chemoselectivity for these reactions by choosing the right conditions for the reaction. Okay, so that brings us to the end of the bioviliga. That's what I wanted to do. Next time we begin in the selective oxidation of alcohols. Okay, I definitely want to keep those annotations. Does anyone have any questions that they'd like to ask?
I don't know if I have a good question or not, but I have one.
Ask away. It doesn't have to be a good question. The only thing that's necessary is a good answer.
Sure. Okay. So I'm used to seeing like hydrogen peroxide and N bonds. Like these are homolytic bonding. So I always associate them with radicals. So how come it's like a heterolytic breakage rather than a homolytic?
That is actually a very good question. So there. It can do homolytic cleavage. It depends on the conditions. If you were to shine UV light on this, yep, homolytic cleavage. If you were to heat the crap out of it, you'd get homolytic cleavage. Now, in terms of peroxides doing homolytic cleavage, the classic one for radical reactions is benzoyl peroxide, which I'm drawing there. Now, under those circumstances, because you have carboxylic acids or carbonyl groups, sorry, at both ends, that of course pulls electron density away from the OO bond. So in actual fact, this bond is even weaker than usual. Okay, there's very little electron density there. It really is a very weak bond. So heating it up, and you don't even need to heat it up a very great deal, would do that. But under the conditions of the reactions we're doing here, there's not strong enough UV light present, or we're not going for high enough temperatures. But yeah, weak bonds for sure. You should always watch out for undergoing homolytic cleavage. These are weak, they're just not that weak. Does that answer your question?
I suppose. And looking at the MO,
Yeah.
usually we associate like the bonding and anti-bonding if they're the same. We associate them with like, I guess, non-bonding or doesn't exist.
Well, this is the thing. This is where it becomes interesting. I think it becomes interesting. So typically, if we're looking at an energy diagram, and as I've actually got lines here, I'll use them. If you've got two atoms of the same energy, you can make a bonding combination like this. Now, the anti-bonding combination is actually more anti-bonding than the bonding combination is bonding. So this is, I'm going to say EA, and this is EB, okay? Anti-bonding and bonding. And EA is greater than EB. Okay? So what that actually means is that typically when two molecules interact and they make a filled antibond, the bond breaks. Okay? Now, in the case that we're looking at here, the bond is a pi bond and the antibond is a pi star bond. Yeah?
Yeah.
Now, because we're looking at the interaction between p orbitals. And if you consider the structure that the canonical structure that we draw for hydrazine, well, we can draw a lone pair down here and a lone pair over here, where they're as far away from each other as they can be. Well, what if I drew that slightly differently? As an antibond. That's got 2 electrons in it, and then there's 2 electrons in the bond, which I'm not showing. The effect is that it looks like 2 lone pairs sitting next to each other because there is no bond between them. But when you do an analysis of the length of the NN bond here, if there are tables of standard atomic radii of nitrogen, for example, or oxygen, if we're looking at those. And the distance here is greater than the atomic radius of 2 nitrogen atoms. Okay? If it was just non-bonding, then the atomic radius would be exactly that of 2 nitrogen atoms. This bond is actually longer, and that is because we've got this little bit of an extra anti-bonding energy here that's actually pushing the 2 nitrogen atoms further apart than they would be if they were just sitting there on their own. So there is actually more anti-bonding character in this molecule than you might guess, which I think is really cool because I'm a nerd. Any other questions? Or does that answer everything? Or does it just open up more questions?
Well, it opens up more interest, but that's well explained. That's all for me. Thank you.
Okay. Any other questions? Okay, then. Well, I will first of all stop recording.